Imagine the scenario. You're handed a plan for a huge project, and someone tells you, straight up, it's impossible.
Yeah.
Not just difficult, but, mathematically, physically impossible.
Right.
That was the actual verdict from senior German military engineers back in late 1944. They
Yeah.
were looking at the Rhine River, a really crucial crossing point.
Yeah, and this wasn't just, an off-the-cuff remark. They had run the numbers. They used their top-tier engineering standards, the absolute best of the time, looked at the river, the debris, everything.
And their conclusion?
It was firm. To rebuild that specific section, we're talking an 800-foot span, strong enough for heavy tanks and constant traffic. Minimum 3 to 4 weeks. Specialized work. That was it.
A physical fact, almost, baked into their whole defensive plan.
Exactly. They banked on it.
And yet, Allied soldiers, this coalition force, they did it. They built a fully working, heavy-duty bridge over that exact spot in 48 hours.
48 hours. It's staggering when you compare it.
Right. A 4-week minimum crunched down into basically a weekend. So this deep dive, it's really about more than just speed. It's about how a different way of thinking completely changed a critical military operation.
That's what we want to dig into today. We're going into the archives, looking at the records, not just what they built, but the how. How did they manage that speed? And maybe more importantly, why were the German engineers so wrong in their prediction?
What did the Germans miss?
Exactly. We're hunting for those surprising details, the key bits of information that show how, ingenuity and maybe a refusal to accept impossible overcame these very rigid calculations, using things like modular design.
And just a different philosophy, maybe.
That's a huge part of it. We'll look at these clashing engineering ideas, permanence versus speed, and how Colonel Day's team pulled off something that really did look superhuman at the time.
Okay, so let's set the scene first. The context here is everything.
Right. To really get why this bridge was so vital, you have to understand the bigger picture. It's late 1944. The Allies are pushing hard, moving east deep into German-held territory.
And momentum is absolutely key at this stage, isn't it?
It's everything. It's not just about gaining ground. It's about preventing the German forces from digging in, regrouping, setting up new, strong defensive lines. Every day counts.
But then there's the Rhine. It's not just any river.
No, it's massive. Europe's historic central artery, really.
Right.
And strategically, psychologically, it's this huge barrier. Near this town, Remagen, it became a bottleneck, a real choke point.
So if the Allied advance gets stuck there...
The whole thing could stall. The entire offensive momentum could just evaporate. That was the danger.
And the Germans knew this. They were counting on the Rhine.
Absolutely. And they had this ingrained belief built up over years in their own engineering superiority. German engineering was seen as, unbeatable, built to last.
The strategy relied on it.
Completely. Fortify the main crossings, and then as they retreated, blow every single bridge. Create this uncrossable gap. That was the plan.
So when their engineers looked at this specific site near Remagen, after the bridge there was destroyed, they weren't just being pessimistic, saying weeks were needed.
No, they were applying what they saw as solid, irrefutable engineering science. They were doing a proper civil engineering assessment.
What factors went into that impossible in under 3 weeks calculation?
Several things. First, the span itself, 800 feet. It's a long way to bridge over moving water.
Especially fast-moving water.
Right. Second, the conditions. The current was really fierce. It wasn't just rain, it was autumn rains plus early snowmelt from the mountains upstream, so the river had serious power.
Okay.
And third, the load. This bridge needed to take the heaviest Allied tanks, Shermans, maybe even heavier stuff coming, plus endless columns of supply trucks, nonstop traffic.
And they crunched those numbers using their standard German methods.
Exactly. Their established engineering codes, which meant things like minimum times for concrete to cure, stress tolerances way beyond what was tactically needed for a short time, safety margins designed for decades of use.
Built for permanence.
That's the core of it. So their 3 to 4 week estimate, it was based on building a proper, safe, permanent bridge according to their rules. That was the physics as they saw it.
But for the Allies, waiting 3 or 4 weeks just wasn't an option.
Strategically, it was unthinkable, a disaster. If they waited that long, the whole initiative could be lost. Supplies would pile up uselessly on the wrong side, troops would be vulnerable.
And the Germans would get a breathing room.
Exactly. Time to build formidable new defenses behind the river. The Allied commanders knew the urgency was absolute.
So the decision was made, we have to do it faster. We have to beat that German timeline.
It was audacious. They basically decided they had to prove the German engineers catastrophically wrong. It wasn't about building a better bridge in the long run, but a functional bridge much, much faster than the enemy thought possible.
But that sounds like a huge risk. What if they rushed it and it failed? A bridge collapsed mid-crossing. That would be even worse, wouldn't it? Trapping troops, losing equipment.
It was a calculated risk, absolutely. But they weighed against the certainty of strategic failure if they waited. They essentially redefined success.
How so?
The Germans defined success as a bridge meeting, say 50-year durability standards. The Allies redefined success as, does it stand up for 48 hours? Can it get the first critical wave of tanks and trucks across? Does it stay stable enough, maybe with constant repairs, to keep the advance rolling for a few crucial weeks?
So speed became the primary engineering driver, not longevity.
Precisely. The absolute necessity of maintaining that offensive pressure just overruled the traditional engineering constraints. They accepted the risk of a temporary, maybe slightly less robust structure to avoid the much bigger risk of letting the war drag on.
Okay, so if the Germans were stuck thinking about traditional construction, the Allies must have had a completely different playbook. How do you squeeze a month's work into 2 days? It has to start with the team itself, right? Colonel Day's unit.
Yeah, the people involved were key. This wasn't your standard peacetime construction crew with decades of civil engineering experience.
Right.
It was a specialized, rapid deployment group, about 300 soldiers in total, a mix of American combat engineers, but crucially, also some British military bridge specialists who were experts in this kind of quick work.
Combat troops, basically.
Primarily, these were fighting men. Their engineering knowledge was forged in the heat of battle, very practical, focused on immediate needs, often involving improvisation and field repairs, not formal theoretical stuff.
And the site itself, you said the Germans left a catastrophe zone. Can you paint a picture of what they walked into?
Oh, it was grim. Imagine steep, muddy riverbanks, probably churned up by shelling. And the river itself just choked with the wreckage of the old bridge. Huge, twisted steel beams, massive chunks of broken concrete, jagged metal everywhere, some visible, some hidden just below the waterline.
We're a real mess.
A dangerous mess. But it wasn't just blocking the way, it was a hazard to the engineers, to their boats, to the bridge components they needed to place. The Germans likely figured it would take weeks just to clear that debris safely before any real building could even start.
And they weren't working in a quiet construction zone. They were under threat.
Constantly, they were building a very obvious, very high-value target, right under the noses of remaining German forces, potentially within range of artillery or mortar fire.
So work around the clock.
Had to be. 247 operations under floodlights at night, probably, always with the risk of attack. Security detachments would be nearby, providing cover, but the engineers themselves were exposed. Plus the physical toll, cold, wet, exhausting work in a high-stress environment.
Okay, so tough conditions, dedicated troops. But the real game changer, the thing the German analysis missed, was modularity, wasn't it?
That's the absolute core of it. The Allies weren't planning to build from scratch on site. The Germans were thinking in situ, pour concrete, wait for it to cure, erect scaffolding piece by piece.
The traditional way.
Right. The Allies, however, were using prefabricated, standardized components. Think of it like a giant, heavy-duty Meccano set or Lego kit.
What kind of components?
Key things were the pontoon sections. These were standardized, sealed steel boxes that floated, forming the base, then pre-cut, pre-drilled steel sections for the framework that went on top, standardized cables for anchoring, and even pre-cut timber sections for the roadway, the decking.
So the genius wasn't just the parts, but getting them there at the right time. The logistics must have been incredible.
Astonishing. This was planned with military precision, miles away from the river. Colonel Day's team on site wasn't worrying about, do we have enough steel beams? They were managing a complex schedule, ensuring that Pontoon Unit C arrived exactly when needed to connect to Framework Section D, down to the hour, almost.
A logistical ballet, as you said.
Pretty much.
And they also had to really understand the river itself. You mentioned studying the hydrology. Why was that so critical, especially with the snowmelt?
Because the river was actively working against them. They weren't just measuring the depth, they had to know the speed and force of that current. The snowmelt made it powerful, strong enough to just rip unsecured pontoons away.
Right.
So they needed precise calculations for anchoring, how strong the cables needed to be, where to fix them, how much tension, and load distribution was vital. If the weight of the first tank wasn't spread correctly across the pontoon,
The whole thing could buckle.
instantly, catastrophic failure. So they had to factor in water flow, potential fluctuations in river level, water temperature affecting materials. all of it, while moving at incredible speed.
So it's this combination, speed from 2047 work and prefab parts, but also extreme meticulousness in the planning and understanding the environment.
Absolutely. Organized chaos might be one way to put it. But underneath, it was highly choreographed. The speed couldn't come at the cost of the fundamental engineering needed for a temporary tactical bridge. They pushed the limits, but they knew exactly where those limits were.
Okay, let's walk through these 48 hours. It sounds like every hour counted. Starts the second they hit the site, right? Phase one is just dealing with the mess.
Exactly. The first, say, 12 hours were all about wrestling with what the Germans left behind. Grueling, dangerous work. Salvage crews using heavy equipment, cutters, chains, trying to clear those massive twisted girders from the river channel.
Because even one hidden piece could wreck a pontoon.
Or destabilize the whole foundation. It had to be cleared, or at least neutralized.
And this is where the divers played a crucial role, under really horrific conditions.
Unsung heroes, definitely. Pitch black water, freezing cold, fast current, and they're down there basically feeling their way around broken concrete and sharp metal.
What were they trying to do?
Two main things. Locate and assess any underwater debris that posed a direct threat, and quickly evaluate the riverbed itself. Find spots solid enough to drive in temporary pilings or secure heavy anchors for the pontoons. Meanwhile, up top, command posts are being set up on both banks. Constant communication, lines of sight for coordination, especially vital once darkness fell.
So 12 hours of intense prep work. Then the actual assembly begins.
Yes, phase two kicks in. The first modular pontoon sections start going into the water, they're launched, and then have to be carefully maneuvered into the precise position against that strong current.
Sounds tricky.
Needs incredible teamwork. These things are big and heavy, even though they float. Small boats nudging them, teams on the bank pulling ropes and cables. Requires immense effort and coordination. And as soon as one is roughly in place, the anchoring starts immediately.
Against that Rhine current, that must have been a constant fight. How did they anchor them securely?
Massive steel cables. Engineers were working right at the water's edge, sometimes partly submerged in that freezing water, making sure each pontoon was securely chained or cabled to the bank, or to heavy anchors sunk into the riverbed based on what the divers found.
And they had to watch the river level, too.
Constantly. If the river rose unexpectedly, even by a few inches, due to more meltwater coming down, it could change all the stresses on the cables and pontoons already in place. They need to adjust tension immediately. It was dynamic.
Okay, pontoons anchored, forming a floating base. Then comes the superstructure, the actual bridge deck.
Right. Now the pre-cut steel beams start going across, spanning from pontoon to pontoon. This needed absolute precision. You couldn't just drop them roughly in place.
Millimeter accuracy.
Pretty much. For the connections to line up, for the load to distribute evenly, welders are working non-stop now, often through the cold night. You can just picture it, the clang of steel, orders being shouted, and these bright, sharp sparks flying everywhere against the dark river. A real hive of activity.
And incredibly, the reports say that around the 24-hour mark, halfway through, they realized they were actually ahead of schedule.
Yeah, and an amazing morale boost, I imagine. But also, probably more pressure. Being ahead meant they had a tiny bit of breathing room, maybe, but they couldn't let up. Still had the whole roadway deck to lay, the ramps to build, every single connection to double-check.
Which leads us to a really telling moment around hour 30, the test of precision versus speed. What happened there?
This really shows the command philosophy. They're pushing hard, the finish line feels close, but a spot inspection by an engineer flags a potential problem, a weld on a critical load-bearing beam. It wasn't quite up to the required tolerance.
Not failing, but maybe not perfect.
Exactly. It introduced a risk factor they weren't willing to accept, even under that immense time pressure.
So what was the call? Just reinforce it and move on?
No. The order came down. Stop work on that section. They had to physically remove the suspect piece, cut out the weld, and redo it properly, to the exact specification.
Wow. That must have cost them time.
It did. Reports suggest it cost them about 3 crucial hours. They had to backtrack, dismantle work they just finished. It pushed them back closer to their original tight schedule.
But that decision says a lot. They prioritized structural integrity over just hitting the clock. Why was that specific weld so important?
Because if that point failed under the immense dynamic weight of a tank crossing, the bridge wouldn't just be damaged. It could collapse, block the crossing entirely, maybe trap vehicles and men, the whole infence of stalls. That failure would cost far more than 3 hours.
So the philosophy was, temporary is okay, but unsafe is not.
Precisely. Acceptable risk on lifespan, Zero tolerance for immediate structural failure under load. That 3-hour delay ensured the bridge would actually work for that critical initial crossing.
Okay, so they fix the weld, get back on track. By hour 36, the main structure is done, the decking is going down, and crucially, the approach ramps are being built to connect the bridge to the riverbanks.
Right, bridging that final gap. And testing started almost immediately. No ribbon-cutting ceremony here.
How did they test it?
Light vehicles first. Jeeps, maybe light trucks, crossing slowly, methodically. Engineers watching like hawks from the banks, looking for any sign of sag, wobble, oscillation, unexpected stress. But the calculations held. The structure was solid.
And the real breakthrough came just a few hours later.
Yeah, around hour 42. The bridge is declared operational. Might still be finishing touches, maybe adding guardrails or something, but it's strong enough for traffic to start.
And it did.
Immediately. No gentle breaking in period. Supply trucks, personnel carriers, more jeeps. They start rolling across. In a way, the actual military traffic became the final continuous stress test. The river crossing was officially open for business.
And the Germans watching this unfold.
Must have been disbelief, then shock. Their own engineers had guaranteed this was weeks away. Now reports are coming in. The bridge is up. It's working. Allied traffic is pouring across.
A major intelligence failure on their
A
part.
huge blow. They apparently demanded photos from reconnaissance planes to confirm it. Seeing those images, that stream of Allied vehicles flowing uninterrupted across the Rhine, it must have been devastating for morale, and it completely upended their defensive planning for that sector. By the 48-hour mark, exactly as planned, the bridge was fully operational, carrying the load. Mission accomplished.
It's an incredible timeline. But the real learning maybe comes from looking back, especially at the German perspective after the war. Why did they think it was impossible?
Post-war debriefings and analysis really highlight the core reason. They weren't just being conservative. They genuinely believed it couldn't be done because they were measuring it against German engineering standards.
And those standards prioritized what exactly?
Longevity, maximum durability, things built for peacetime, essentially. Think about permanent infrastructure.
Okay, break that down. What does peacetime methods mean in practice here?
It means things like specifying minimum concrete curing times, days, sometimes weeks, to ensure absolute maximum strength, regardless of whether you need that maximum strength right now. It means designing with huge safety factors, maybe 50% or even 100% over the expected load, to account for decades of wear, weather, unforeseen stresses.
Building for 50 years, not 50 days.
Exactly. They were thinking about building something that would last generations. That was their default engineering philosophy.
Whereas the Allies, driven by immediate need, had a totally different goal.
Completely different. Their bridge only needed to survive long enough to support the main push across the river. Maybe weeks, maybe a couple of months at most, until more permanent crossings could be established further upstream or downstream.
So they could accept a bridge that might need constant maintenance.
Yes. They accepted a structure that probably wouldn't meet any civilian building codes, might have needed daily checks and repairs, might not last a hard winter. But crucially, it could handle the required military traffic safely for the immediate tactical window.
How did they achieve that trade-off? Less concrete.
Much less reliance on concrete where possible. Heavy use of steel components, bolted or welded together quickly, using those prefabricated parts. Standardized connections. It was all about speed of assembly, trading that long-term, over-engineered durability for immediate temporary functionality.
So the Germans weren't wrong about how long it would take to build a German-style bridge. They just couldn't conceive that the Allies would choose to build a different kind of bridge altogether.
That was their blind spot. They assumed the Allies would play by the same rule book, the same prioritization of permanence. That difference in perspective, that flexibility, was the key Allied advantage here.
Wasn't necessarily better materials or technology.
No, not fundamentally. It was a better, or at least more adaptable, engineering doctrine for wartime. They were solving the problem within the real constraints of the war, not the constraints of traditional civil engineering practices.
And the impact of getting that bridge up so fast was huge, wasn't it? It stayed operational for quite a while.
Much longer than perhaps even they expected, over 2 months, carrying a massive volume of traffic. It became this vital artery, this umbilical cord feeding the advance deep into Germany.
Tanks, troops, fuel, ammo.
Everything. Without that bridge, the momentum definitely would have slowed, maybe stalled.
Yeah.
Many historians argue that getting that crossing open so quickly, maintaining that relentless pressure, likely shortened the war in Europe by several weeks.
Wow, weeks. That's significant.
Hugely significant.
And beyond the pure logistics, there was the psychological win, shattering that myth of German engineering invincibility.
Absolutely. It was a major blow to German confidence, both military and civilian. And conversely, a huge boost for the Allies. It showed they could match and even surpass German technical prowess through ingenuity, speed, and sheer determination under fire. Colonel Day's team and their achievement became legendary.
A case study for military engineers ever since.
Definitely. Taught in academies worldwide as a prime example of rapid construction, engineering under pressure, and crucially, the importance of questioning assumptions about what's impossible.
So if we bring this back to the listener today, what's the enduring lesson from this 48-hour miracle?
I think the core takeaway is that impossible is very often not a statement about physics, but a statement about assumptions and accepted parameters. The Germans said impossible based on their parameters: permanence, peacetime standards, traditional methods.
The Allies didn't change the laws of physics?
No, they changed the requirements. They didn't need a 50-year bridge. They needed a 2-month bridge. By discarding the unnecessary constraints of permanence, the impossible suddenly became achievable.
They redefined success for the specific context.
Exactly. It wasn't about cutting corners on safety for the immediate task, but about eliminating requirements that were irrelevant to that task. It's about asking, what assumptions are baked into this claim of impossibility? Are those assumptions actually fixed, or can we change them?
A powerful idea for any kind of problem solving, really, whether it's engineering, business, or anything else. First, question the constraints.
Find the hidden assumptions. That's often where the path to achieving the impossible lies. #outro.
It really is an incredible story when you break it down. An 800-foot bridge across one of Europe's most powerful rivers, built while being shot at, strong enough for tanks, and done in just 48 hours.
A testament to ingenuity, planning, and sheer grit. And for anyone wondering, the bridge did its job. After the immediate need passed and the war moved on, it was eventually dismantled. The materials were recovered, repurposed. Its physical presence was temporary, as intended.
But the achievement itself, the lesson learned, that certainly endured. So maybe the final thought to leave you, the listener, with is this. The next time you hear something described as impossible, maybe a deadline seems impossible, a budget, a technical hurdle. Think about that 48-hour bridge over the Rhine. Ask yourself, what are the hidden assumptions in that impossible? What rules are being taken for granted? Are we talking about building for permanence when maybe, just maybe, something functional and temporary is actually what's needed right now?
What happens if you're willing to change the parameters, to question that conventional wisdom?
Because maybe impossible just means, as you said, impossible under the current unquestioned rules.
It often does. It might just mean we haven't been forced or dared to change the rules yet.
A fantastic perspective. Thanks for taking us through this deep dive today. Truly fascinating stuff.
My pleasure. It's a great story.
We'll see you next time for another deep dive.